Data science interview questions, statistics. Data science interview questions, statistics. What is central limit theorem and why is it important? The central limit theorem is a fundamental concept in statistics that states that when independent random variables are added, their sum tends towards a normal distribution, regardless of the shape of the original variable's distribution. In other words, the CLT states that the sampling distribution of the mean or the sum of a sufficiently large number of independent and identically distributed, that is IID, random variables will be approximately normal distributed regardless of the shape of the population distribution. CLT is important for several reasons. First is foundation of inferential statistics. The CLT is the basis for many statistical techniques used in hypothesis testing and confidence interval estimation. It allows us to make inferences about the population parameters based on sample data. Second, approximation of population distribution. The CLT enables us to approximate the distribution of a sample mean or sum with a normal distribution, even if the underlying population distribution is not normal. This is particularly useful because the normal distribution is well understood and has many desirable properties. Third, sample size determination. The CLT helps in determining the sample size required for statistical analysis. It provides guidelines on the minimum sample size needed to make valid inferences about the population mean or sum. Number 4. Statistical modeling. The CLT is often used as a theoretical justification for assuming normality in many statistical models. It allows us to apply parametric techniques that assume normality, such as a linear regression or analysis of variance, that is ANOVA, to a wide range of practical situations. Overall, the central limit theorem is a crucial concept in statistics, as it allows us to make valid inferences and apply statistical techniques even when underlying population distribution is unknown or non-normal. It provides a bridge between characteristics of sample and the properties of population, making it a cornerstone of statistical theory and practice. What is sampling? How many sampling methods do you know? Sampling is the process of selecting a subset of individuals or items from a larger population in order to gather information or make inferences about the entire population. Instead of studying or analyzing every single individual or item in population, sampling allows us to study a representative subset, which is more practical and cost effective. There are several different sampling methods commonly used in statistics. Here are some of the main ones. Random sampling. In this method, each individual or item in the population has equal chances of being selected. It involves randomly selecting sample without any specific criteria or stratification. Stratified sampling. Stratified sampling involves dividing the population into subgroups or strata based on certain characteristics, age, gender, location, etc. Then selecting samples from each stratum in proportion to their representation in the population. This ensures that each subgroup is adequately represented in the sample. Systematic sampling. Systematic sampling involves selecting every nth individual or item from population after randomly selecting a starting point. For example, if the population size is n and a sample size of n is desired, every n by nth individual is selected. Cluster sampling. Cluster sampling involves dividing the population into clusters or groups and then randomly selecting entire cluster as the sampling unit. This method is useful when population geographically dispersed, and it is more practical to sample entire clusters instead of individuals. Convenience sampling. Convenience sampling involves selecting individuals or items based on their easy accessibility or availability. This method is often used for quick and easy data collection but may introduce bias as the sample may not be representative of population. Snowball sampling. Snowball sampling is a non-probability sampling method where initial participation are selected and then they help in recruiting more participants from their network. This method is often used when the population is hard to reach or locate. These are just a few examples of sampling methods, and there are variations and combination of these methods as well. The choice of sampling method depends on various factors including the research objectives, population characteristics, available resources, and practical constraints. Each sampling method has its strength and limitation, and it is important to select an appropriate method that best suits the research goals and ensures a representative and unbiased sample. What is the difference between type 1 versus type 2 error? Type 1 and type 2 errors are concepts related to hypothesis testing in statistics. They represent the two types of errors that can occur when making decisions based on statistical tests. Type 1 error, also known as false positive. A type 1 error occurs when the null hypothesis is rejected, even though it is true. In other words, it is incorrect rejection of a true null hypothesis. The significance level alpha of a statistical test determines the probability of making a type 1 error. For example, if the significance level is set at 0.05, it means that there is a 5% chance of committing a type 1 error. Type 2 error, also known as false negative. A type 2 error occurs when the null hypothesis is not rejected, even though it is false. In other words, it is the failure to reject a false null hypothesis. The probability of making a type 2 error is denoted as beta and is related to power of a statistical test. Power is the probability of correctly rejecting a false null hypothesis. Therefore, type 2 error is equal to 1 minus the power of test. To summarize, type 1 error, rejecting a true null hypothesis. False positive. Type 2 errors, failing to reject a false null hypothesis. False negative. The relationship between type 1 and type 2 errors is often inverse. By decreasing the probability of one type of error, the probability of other type of error increases. This relationship is influenced by factors such as sample size, effect size, and chosen significance level. In hypothesis testing, it is important to strike a balance between type 1 and type 2 errors. The significance level and desired power of a test need to be determined based on a specific context and consequences associated with each type of error. True positive, false negative, true false, and false positive. And this is the table. No reject H null hypothesis, that is H naught. Reject hypothesis, null hypothesis. H naught is true and H naught is false. So in first column we can see that this is a no reject null hypothesis, and second column there is a reject hypothesis, and in first column and second row we say H naught null hypothesis is true. The true negative, then false positive, first type of error, that is false positive, and false negative, that is second type of error. What is a linear regression? What do the terms p-value coefficient and r x0002 squared value mean? What is the significance of each of these components? Linear regression is a statistical modeling technique used to analyze relationship between a dependent variable and one or more independent variables. It assumes a linear relationship between the variables, aiming to find the best fitting straight line that minimizes the differences between the observed data points and the predicted values. Now let us discuss the terms related to linear regression. P-value. In linear regression, the p-value measures the statistical significance of the coefficient. It indicates the probability of observing a coefficient as extreme as the one calculated. Assuming that the null hypothesis is true, there is no relationship between independent variable and dependent variable. A low p-value, usually below a significance level like 0.05, suggests that the coefficient is statistically significant and provides evidence against the null hypothesis. Coefficient. In linear regression, coefficient represent the estimated changes in dependent variable associated with a one unit change in corresponding independent variable, assuming other variables are held constant. They indicate the direction and magnitude of relationship between the dependent variable and the dependent variable. Each independent variable has its own coefficient in the regression equation. R squared value. R squared is a measure of a goodness of fit of a linear regression model. It represents the proportion of variance in the dependent variable that is explained by the independent variable. R squared ranges from 0 to 1 with a higher value indicating a better fit. Higher value of R square, it means it is a better fit. However, it does not indicate the causality of relationship or the predictive power of the model. It should be interpreted alongside other statistical measures and the context of analysis. The significance of these components in linear regression is as follows. P-value. The p-value helps determine statistical significance of relationship between independent variables and the dependent variable. A low p-value suggests that the relationship is unlikely to be due to chance and provides evidence in favor of significance association. Coefficient. Coefficient provide information about the direction, positive or negative, and magnitude of effect of independent variables on the dependent variable. They quantify the relationship and help understand the impact of each independent variable on the outcome. R squared value. R squared measures the proportion of variance explained by independent variables. It provides an indication of how well the model fits the observed data. A higher R squared suggests that a larger portion of the variation in the dependent variable is explained by independent variable. These components collectively contribute to interpretation and evaluation of linear regression model, aiding in understanding the relationship between variables, assessing significance, and assessing the overall fit of model to the data. Question number 5. What are assumptions required for linear regression? Linear regression relies on several assumptions to ensure the validity and accuracy of model results. These assumptions are as follows. 1. Linearity. Linear regression assumes a linear relationship between independent variables and the dependent variable. The relationship should be additive, meaning that the effect of each independent variable is constant across all levels of other independent variables. Number 2. Independence. The observations used in linear regression should be independent of each other. These assumptions ensure that the errors or residuals in the model are not influenced by the values of other observations. Number 3. Homoscedasticity. Homoscedasticity, or the assumption of constant variance, implies that the spread of residuals should be consistent across all the levels of independent variables. In other words, the variability of error should be constant along the regression line. The variability of error should be constant along the regression line. Number 4. Normality. Linear regression assumes that the residuals or errors follow a normal distribution. This assumption allows for use of statistical tests and confidence intervals based on the normal distribution. No multicollinearity. Linear regression assumes that the independent variables are not highly correlated with each other. Multicollinearity occurs when there is a strong correlation between independent variables, making it difficult to separate their individual effect on dependent variable. No endogeneity. Number 6. The assumption of no endogeneity states that there should be no relationship between the errors and independent variable. Endogeneity can arise when there are omitted variables or when there is a simultaneous causality between dependent and independent variables. These assumptions are important to consider when applying linear regression. Violations of these assumptions may lead to biased are inefficient estimates, unreliable inferences, and inaccurate predictions. It is advisable to assess these assumptions through diagnostic tests and visualization to ensure the validity of linear regression results. Question number 6. What is a statistical interaction? A statistical interaction, also known as interaction effect or interaction term, occurs when effect of one independent variable on the dependent variable varies based on level or value of another independent variable. In other words, the relationship between dependent variable and one independent variable depends on the presence or value of another independent variable. Interactions are an essential concept in statistical analysis as they provide insights into how the effects of variables may change depending on different conditions or contexts. Interaction allows us to examine the combined effect of two or more variables on the dependent variable, which may be different from what would be expected based on individual effect of each variable alone. To understand interactions, let us consider an example of a study examining the effect of new drug on blood pressure. The researchers are interested in determining if drugs' effect on blood pressure differs based on age of the patient. They include two independent variables, drug doses and patient age. They also measure the dependent variable, which is blood pressure. If there is an interaction between drug doses and patient age, it means that the effect of drug doses on the blood pressure is different for different age groups. For example, the drug may have a stronger effect on reducing blood pressure in older patient compared to younger patient, indicating an interaction effect. To assess interaction, researchers often use statistical techniques such as analysis of variance or regression analysis. They can include interaction terms in their models to quantify and test the presence of interaction. The significance of interaction term indicates whether the relationship between the variable is statistically significant. The interactions are important because they allow for a more nuanced understanding of how variables influence each other and the dependent variable. They help identify situations where the relationship between variables is not constant across all levels, providing insights into complex nature of the phenomena under study. Interactions are commonly explored in fields such as psychology, social sciences, economics, and medicine, among others, to gain a deeper understanding of factors that impact outcome of interest. What is selection bias? Selection bias refers to a systematic error or distortion that occurs in a research study when participants or subjects selected for the study are not representative of the target population. It arises when the process of selecting participants introduces a bias that skews the sample in a way that is not representative of larger population from which it is drawn. This bias can significantly impact the validity and generalizability of a study's findings. Selection bias can occur in various ways, such as non-random sampling, self-selection bias, survivor's bias. Number 1. Non-random sampling. When the selection of participants is not done randomly, certain groups within the population may be overrepresented or underrepresented. This can lead to a sample that does not accurately reflect the characteristics of target population. Self-selection bias. When individuals have the choice to volunteer or opt in to participate in a study, those who choose to participate may have different characteristics or motivations compared to those who do not. This can lead to a sample that is biased and not representative of population. Survivorship. It occurs when the analysis or conclusions are based only on individuals or subjects who have survived or completed the study, excluding those who dropped out or were lost to follow up. This can introduce bias by excluding certain individuals with different characteristics or outcomes. Number 4. Berkin's bias. It occurs when the selection of participants is based on their presence or absence in a healthcare setting such as hospital. This can lead to biased result if exposure or outcome under study is related to hospital admission. The presence of selection bias can distort the study result and limit the generalizability of findings of broader population. It can lead to overestimation or underestimation of true association or effect being studied. Proper sampling method and a careful consideration of potential biases are crucial to minimize selection bias and improve the validity of research finding. Various statistical techniques and study design strategies such as random sampling and stratification can help mitigate selection bias and improve the accuracy and representativeness of study results. Question number 8. What is an example of dataset with non-Gaussian distribution? A non-Gaussian distribution, also known as a non-normal distribution, refers to a dataset in which the values do not follow a Gaussian or normal distribution pattern. In a Gaussian distribution, the data is symmetrically distributed around the mean, with majority of values concentrated around the mean and tapering off toward the tail. There are numerous examples of datasets that exhibit non-Gaussian distribution. Here are a few examples. Number 1. Skewed distribution. A skewed distribution occurs when the data is asymmetric, when the data is asymmetric, meaning it is stretched or elongated in one direction. An example is an income distribution where a large number of individuals have relatively low incomes, but there are a few individuals with high incomes, causing the distribution to be skewed to the right. Bimodal distribution. Number 2. A bimodal distribution has two distinct peaks or modes. This means that the data set has two different groups or subpopulations with different characteristics. An example is a high distribution in a population that includes both adults and children. The data may exhibit two peaks corresponding to different height ranges of adults and children. Number 3. Multimodal distribution. A multimodal distribution has more than two distinct peaks or modes. This suggests the presence of multiple subpopulation or categories within the data set. An example could be a survey measuring satisfaction levels of customers in different industries. Each industry may have its own distinct mode of satisfaction ratings. Number 4. Exponential distribution. An exponential distribution is characterized by a constant rate of decay. It is commonly observed in situations where the time between events follow an exponential pattern, such as the time between customer arrival at a service desk or the decay of radioactive substances. Number 5. Power law distribution. A power law distribution is characterized by a long tail where the frequency of occurrences of values decreases rapidly as the values increase. Example of power law distribution include distribution of city population, the distribution of income, and the distribution of website page views. These are just a few examples of data set with non-Gaussian distribution. It is important to remember that in real-world data, distributions can take various forms, and understanding the underlying distribution is crucial for appropriate statistical analysis and modeling. Thank you.